Hello. In the previous lecture we saw the single parity check decoder for the 3,2 case, and we saw this min sum approximation, and we saw an illustration of how these things happen for some simple examples and particular scenarios. So, in this lecture we will extend this idea to longer codes. Instead of 3,2, if you have n minus 1, okay, then what do you do? How do you do this? Okay, so it turns out it's quite easy to extend, but I want to describe that in this lecture. Okay. So, the picture is similar to before, except that we are using n minus 1. So, you have a message vector which is m1 m2 till n minus 1, and then you do the single parity check code, which will give you a code word C, which if I say C1 C2 till Cn, we know how this is done. C1 equals m1, C2 equals m2 dot till Cn minus 1 equals mn minus 1, and then Cn becomes C1 XOR C2 XOR Cn minus 1. So, this is the single parity check code, and then you do BPSK, and then you get received values, this is noise, you get received values R1, R2 to Rn, and then you have a SISO decode, and you put out capital L, which is L1, L2, Ln. This is also L plus Lxt, okay, and what is L? L is 2 by sigma squared times R, and this Lxt is the critical calculation. Okay, so how do we calculate this? We know how to do this. Lxt 1 is basically sine of L of 2 times sine of. So we saw for the 3,2 case, for the extrinsic value for the first bit, you find the product of the signs of L of 2 and L of 3, and then you take the minimum of the absolute value of L of 2 and L of 3. Okay. So, it turns out the same thing extends for a longer single parity check code. Okay. So, I will first provide what the answer is, and then go into details of how that comes up. Okay. So, what is Lxt 1? So, this is simply the product of the signs of all the remaining channel LLRs, and then minimum of absolute value of all the L of n. Okay. So, just like we had for 3,2 for the first extrinsic, we took all the remaining values, multiplied their signs, and took the min of the absolute values. So, likewise when you have n minus 1 for the extrinsic value for the first bit, you simply take the remaining LLRs, multiply them, and then take the minimum of the absolute values for that also. Okay. So, this is Lxt 1. So, what is Lxt 2? So, it does not vary too much from this. You take sine of L of 1, sine of L of 3, you drop the second L of 2, then after that it is all going all the way till the end, and then the absolute value is min of absolute value of L of 1, absolute value of L of 3, so on till absolute value of L of n. Is that okay? So, that is what you do for the second extrinsic value. Okay. So, likewise you can go on. What happens for the last extrinsic value? You will only take the first n minus 1, and then minimum for the first n minus 1. Okay. So, this is quite a reasonable extension. So, because if you see when you do Cn, you have C1 XOR C2 XOR so on till, maybe I should write a few more terms here. Okay. So, XOR C3 XOR C4 so on till XOR Cn minus 1. Okay. So, first you have C1 plus C2, Okay, so we know how to deal with C1 plus C2. We do minimum of those two LLRs and product of the signs, and then you have that XORed with C3. So if you look at what is going on here, min of absolute value of L of 1 comma absolute value of L of 2, and then if you take min of that with absolute value of L of 3, that is the same as the overall minimum, right. Okay. So, it is enough if you take the minimum of all of the every other input LLR other than the first, other than the nth one in this case. Okay. Same thing happens with the sign. So, you do sine of L of 1 times sine of L of 2 and then multiply that with the sine of L of 3. It is the same thing as multiplying all the signs together. Okay. So, extending from 3 comma 2 to n comma n minus 1 is sort of immediate as far as the SISO decoder is concerned. Okay. Now, it seems here that you are doing a lot of operations. Okay. And it turns out one can simplify this in a very nice way. Okay. So, this is quite important, and this is how people implement the actual decoder. So, first is with the sign. Okay. So, what people would do is you would first find the product of all the signs. Okay. Sine of L of 1, sine of L of 2, sine of L of 3, so on till sine of L of n. Okay, you find the product of all the signs. Okay, so that is one number. So, the sine of Lx1 is actually s times sine of L of 1. Okay, why is this true? Okay, if you take s and multiply with sine of L of 1, what happens? You get sine squared of L of 1 and all these other things. What is sine squared of L of 1? Sine square of x is actually 1. Okay. Why is that? If sine is minus 1, sine into sine becomes plus 1. If sine is plus 1, everything is plus 1. Okay. So, sine squared becomes 1, so that goes away. Now, this is actually true for every sine. So, in fact, sine of Lx2 is simply s times sine of L2 and so on. Okay. Sine of Lxn is s times sine of L of n. Okay. So, this is easy enough, the sign is taken care of. Okay. What about the absolute value? It looks like you have to find so many minimums for every extrinsic. You have to find the minimum of n minus 1 things. Okay. So, it turns out one can rationalize that as well. Okay. So, what you have to do for that is you find first of all m1, which is the min of absolute value of L of 1, absolute value of L of 2, so on till absolute value of L of n. Okay. So, this is the overall minimum absolute value. This is m1. Okay. And then you also find the position of this, which is the argument of min of L of 1. Okay. What do we mean by position of the argument? So, out of these n values, the minimum will occur in some ith position, right. So, that is this pos. Where does minimum occur? Okay. So, this pos could be 1 or 2 or 3 all the way up to n, any one of these values. Now, you might say, okay, there may be two values which are equal. Okay. If two values are equal, you take any one of those to be pos. Okay. So, it does not matter if both 1 and 2 are the same, L of 1 and L of 2 are the same, you can take any one of them to be this value of pos. So, I have the overall minimum m1 and then the position where that overall minimum occurred. Okay. And then I also need the overall second minimum. Okay. So, what is this? This is m2, let me call it. This is min of, so I will write it like this. So, it should be clear to you hopefully. So, L of 1, L of 2 all the way till L of pos minus 1, okay, and then L of pos plus 1 till L of n. Okay. So, this is the overall second minimum. So, what is going on here? I find the overall minimum and then find out where that minimum occurs, and then I knock out that value. Okay. So, I take that L of pos and throw it out. Remember, L of pos is m1 equals L of pos, right. So, that is the point here, where does the minimum occur. So, I find where the first minimum occurs and throw it out, and among the remaining values find the minimum again. So, this is the overall second minimum, and that is m2. Okay. Is that okay? So, this is the idea. So, you take all the incoming LLRs, take their absolute values, find the overall first minimum where it occurs, then throw it out, find the overall second minimum. Okay. Then once you do this, it turns out this absolute value of Lx pos equals m2, and then absolute value of Lx I for I not equal to pos is m1. Okay. So, this is the main result that you can have. Okay. So, think about why this is true. So, what is the absolute value? Absolute value is absolute value of Lx is basically the minimum absolute value of all the remaining guys. Okay. Now, there is an overall minimum and an overall second minimum. For the position of the overall minimum, the absolute value, extrinsic absolute value is actually the overall second minimum, and for every other position, the absolute value of the extrinsic LLR is the overall first minimum. Okay. So, that is the idea, and you can think about why this is true, but it will work out. Okay. So, one can find the absolute values very easily, one can find the signs very easily. In fact, what is going on here is, so S could be either +1 or -1, right. Okay. If it is +1, so you see sign of Lx I is equal to sign of Li, right. If it is -1, sign of Lx I is minus sign of L of I. Okay. So, this is the interesting part here, S gets multiplied by the sign. So, once you find S, once you find the absolute value, you either flip all the signs or you do not flip all the signs. Okay. If the S is negative, S is -1, you flip the signs, otherwise you do not flip the signs. Okay. So, this is the basic operation for the SISO decoder for the single parity check code. Okay. Hopefully, this is clear to you. Once again, let me repeat. When you have the n-1 single parity check code, how do you do the SISO decoder? You compute the intrinsic LLR first. This is the channel or intrinsic LLR 2 by sigma square times r, and then from that you compute the extrinsic LLR. Now, how do you find the extrinsic LLR? We will use the min sum approximation, we are not going to do anything else. First you find the product of the signs of all the LLRs, okay, that is your S. This could be either +1 or -1, and then you find the absolute value of the extrinsic information. How do you find the absolute value of the extrinsic information? You find the overall minimum and its position and the overall second minimum. The absolute value for the overall minimum position pos is actually m2, the overall second minimum, and for all other values the absolute value is the overall minimum m1. Okay. That is the important thing to realize here. And then how do you do the sign? If the overall product of the signs was +1, you retain the signs as it is, same as that of the channel LLR, but in case the S is -1, you flip all the signs. Okay. So, what I am going to do next is take some sample noise values and illustrate how this decoding happens. Okay. So, it's quite important that we see a few of these decoders and how they work, how these values occur, and so on. Okay. And we will stick to this simple min sum approximation. Okay. So, let me clear this up. Okay. So, I am going to let the received value, so I am going to take all ones, okay, so as my code word. So, what am I doing here? So, I am fixing my message to be all 0, okay. So, this is actually a usual thing to illustrate, and you can always fix the message to be all 0. You can take something else as well, but usually all 0 is good enough. Okay. I am fixing my message to be all 0, which means the code word is also all 0, okay, and the symbol vector is always +1s. Okay. But of course, the noise will vary, so you will get them. Okay. So, what about n? Let us take n to be, I don't know, 6, seems like a nice number to take, and then r is 1 plus, so I need a sigma value, so I will stick to the same value as before, 0.8 rand n of 1 comma n. So, this is the received value. Okay. So, you get all these values 1.58, 0.94, there is no noise in this one, Maybe I can try one more. Okay, maybe I can try one more. There's noise, but there's no error in the hard decision decoding. Okay, there you go. You got an error. It's a pretty big error in some sense. Let's see what happens here. Okay, so that's one of the R's. So okay, so this one looks a bit more reasonable. So let's take this to be the received vector. Okay, so you see different values of R will give you different illustrations of the decoder. So I'm just trying to find a good value of R, so that good values of the received vector, so that we have a good illustration. So let's look at this received value R here, 1.26, 0.39, 2.09, minus 0.36, 0.91, 0.80. Okay, so there is an error, so something will happen. Okay, so the first is to calculate L. L, as you know, is 2 by sigma square times R. Okay, so we get this. Okay, 3.93, 1.23, 6.55, so on, so on, so on. Okay, and then what do? We need to do Lxt. For Lxt, I need the product of the signs, right? So if you do sine of L, you get the signs 1, 1, 1, minus 1, 1, 1, and then you can write down capital S as the product of sine of L. Okay, that's minus 1. Okay, I could have also told you that, but still, just to illustrate, we do this. Okay, and then we now have to find the absolute values, right? So absolute value and the minimum absolute value. Is that right? So MATLAB has a lot of functions for this kind of a thing. So you can do, for instance, m1 comma pos equals min of abs of L. So this tells you that the minimum value occurred at the 4th position, 1, 2, 3, 4, and the 4th position is 1.1537. Okay, that's pretty decent. You see that that's the minimum value, and it's the 4th position. Okay, so how do I find m2? M2 is min of abs of L, but L I want 1 colon pos minus 1, and then, so I need to do this, put it into brackets, pos plus 1 colon n, isn't it? So minimum of everything else other than the first minimum. So that's m2. Let's check once again that that's correct. So you see m1 is the first minimum, it's this 1.15379 in the 4th position. M2 is the second minimum, and that's 1.23. Okay, so what do I do for Lxt? So remember, Lxt is mostly going to be m1, so you can let Lxt be simply m1. So how do I do m1 here? It's just m1, 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 except for the 4th position. Okay, mostly going to be m1 except for the 4th position where I have to put m2, okay, and then m1, m1. Is that okay? So that is the absolute value of Lxt. Okay, so this is the absolute value of Lxt, but I also need signs, right? So how do I do signs? I have this overall sign S, okay, and then I also have to multiply with the sign of L, right? So I can take sign of L dot into this guy. Okay, so what is going on here? Once again, I am finding multiplying S with the sign of L. Okay, so that gives me the individual signs, and then dot into each sign is getting multiplied by the absolute value. I have put m1, m1, m1 for the first 3 guys, and wherever the first minimum occurs, I need m2, and then m1, m1 throughout. So this is my Lxt. So that's how it looks. Is that okay? So the extrinsic LLR will look like this. Most of the values will all be equal, and then at least the minimum, first minimum location alone will be different, the second minimum will come, and the signs will get flipped or not depending on whether the overall parity is satisfied, whether the overall product of the signs is positive or not. If the overall product of the signs is negative, then all the signs get flipped, otherwise none of the signs get flipped. Okay, so once again, look at this, how this calculation has gone. We found the overall sign, and then the sign of each input LLR, and then flipped all the signs, and then the absolute value is found by the minimum absolute value, minimum 2 absolute values. Most of the values get replaced by the least of the absolute values, and then the position of the least alone gets replaced by the second least absolute value. Is that okay? So, this is the min sum approximation. So, if you want to do capital L, you can do L plus Lxt, and you see that is the overall output LLR, and this has corrected the error. Is that okay? So, that was a illustration of how the single parity check code works for a larger block length, and hopefully you can see this and repeat it for other cases also. Okay. So, this is the end of this lecture. To summarize, we have seen how to do SISO decoding for the single parity check code, and we see that it's easy. It's quite easy to implement even for long block lengths. It just involves finding minimums and product of signs, etc. It's not very expensive at all in terms of computation. Now, the next important thing is, how is this going to be an ingredient in a decoder for a larger code? Okay, so like I said, single parity check code is not very good in correcting errors. It can correct no errors in fact, and maybe in some cases it can correct errors, but in many cases it cannot correct errors. The minimum distance is not good enough. Minimum distance is very small. So, in reality, people use longer codes with lower rate. Okay, so for instance, rate half. If you look at it, you might have a 2000, 1000 code. Okay, it might be a very large code. And how do you use a single parity check as a ingredient in building a decoder for a larger code? Okay, so in particular, a low density parity check code. Okay, so how this decoder is used as an ingredient in decoding LDPC codes is the next topic, and we'll take it up in the next lecture. Thank you very much.